Hey everybody, it is Friday, September 25th. Um, as you can see there in the aim today, it says, how can we use our knowledge of constant velocity motion to represent motion in different ways? And we are going to get to that. But as I'm sure you remember from yesterday, with the chase problems, we left on a bit of a cliffhanger as to how you go about solving a chase problem using a nice little shortcut. Um, and so let's take a look at how you can use that shortcut to solve a chase problem. A police officer is sitting on the side of the road with a radar gun pointed at the oncoming traffic. In a 40 meter per second speed zone, a motorist zooms past the police officer at a speed of 57 meters per second. As soon as the officer measures the motorist's speed, the officer begins to accelerate in order to pull the motorist over. Once the police officer has reached a sufficient chase speed, 73 meters per second, the speeding motorist is 450 meters ahead of the officer. And the question says, how far must the officer travel before he or she catches up to the motorist? The secret shortcut is real nice. And so I want to show you that now very quickly. We will talk more about this if you would like. You know how when you're in a car and you're looking at another car driving past you, they don't look like they're actually going that fast? You know, they're kind of moving by you very slowly. And like also, if you're in a car and someone else is in a car right next to you, you move along together. So when you look across, it doesn't actually look like they're moving at all because they're always just right there next to you. That's what this method is based on. If the police officer and the motorist were both traveling at whatever that speed was, 57, there would be no relative motion between them. But because everybody views themselves at rest, right? Like when you're sitting in your car seat in a car that's going 60 miles an hour, everything in your car along with you see as being at rest. From the point of view of the motorist, they're at rest. And instead of the police officer traveling at 73 meters per second, for them, the police officer only looks like they're traveling at 16 meters per second, which is the difference between these two speeds, which we call the relative velocity. So relative to the motorist, the police is only going 16 meters per second, or 16 meters per second faster than the motorist. And so, from the motorist's perspective, this gap distance, the distance between them, which I'm going to call d gap now, is being closed, so to speak. It's getting smaller and smaller as the cop catches up to the motorist. That gap is getting closed at the relative velocity, which in this case is 16 meters per second. So just as a little note here for the shortcut, we can also think of this problem as a relative velocity problem. Where the behind person other quotes, closes the gap at the relative velocity, which is the difference between the two speeds. So we can also think of this problem as a relative velocity problem, where the person who's behind, or the behind person, closes the gap at the relative velocity, which is the difference between the two speeds. So let's see how that works. Well, the gap distance is 450 meters. The velocity, the speed of the motorist is 57 meters per second, right? 57 meters per second. The velocity of the police officer is 73 meters per second. And we're going to look for the relative velocity first. So, pretty easy. The relative velocity, which I'm going to label as VREL, is the velocity of the police officer. It's always just bigger minus smaller, minus the velocity of the motorist. And so that number is going to be 73 meters per second minus 57 meters per second. And that's 16 meters per second. And so since the officer closes that gap distance, at the relative velocity, we can find how long it takes to do that. And since V equals d over t, we can say the relative velocity is equal to the gap distance divided by the gap time. And so that means the time to close the gap is going to be d gap over the relative velocity. So we have 450 meters for our gap distance over our relative velocity, which is 16 meters per second. And 450 meters divided by 16 meters per second is 28.125 seconds. And I'm just going to leave that number like that for now. And so to finish this particular method off, if I know the speed the police officer is traveling, 73 meters per second, and now I know how long it takes the police officer to catch up to the motorist, I can answer the question they asked, which is how far does the cop have to go before they catch up to the motorist? And so, if V police is equal to D police over this gap time, then that means the distance, the distance for the police equals VP times T gap. And that would be 73 meters per second times the gap time, which is 28.125 seconds. And what do you know? 73 times 28.125 seconds is 2,053.125 meters, which is approximately equal to 2,100 meters. That's a really powerful and intuitive shortcut. And it serves as a good check. It serves as a good way to do the problem. And is really just pretty clear overall, I think. The only warning I want to give you about this shortcut is that it can give you a little trouble if you don't realize that it doesn't work nicely in every situation. So as you go through this, you want to be careful in thinking about when it works well and when it doesn't. All right, so I'd hope we could all agree that that is, in fact, a nice little shortcut for how to solve some of these chase problems. I want to be very clear, though, about one point, and that is the shortcut lends itself very nicely to examples like this, where we have the police officer chasing the motorist, where the gap distance is given, but it does not necessarily lend itself to problems where the gap distance is not given, because then you'd have to find it. And secondarily, despite the fact that I am showing you this shortcut, and I think it's a good thing to think about, I think there are some good concepts involved in the use of that shortcut, I do think it is a smart idea for you to not become overly reliant on it. I don't think you should use the shortcut as an excuse to not learn like the official method for solving chase problems. And so I wanted to show it to you because I think it's valuable, but I also think the original method is valuable too. And so frankly, I kind of want you to get comfortable with both and use both as you see fit. All right, so as I mentioned at the end of yesterday's video also, I wanted to show you two examples, which I did yesterday, but we didn't get to the shortcut. And then I wanted you to solve one of these chase problems on your own. So here's the problem. Notice it's labeled independent practice. I want you to pause the video when I'm done reading this and try it on your own. It says here, in a swimming race, a father gives his 4-year-old son a 10-second head start. The pool is 25 meters long. The child swims at 0.80 meters per second, while the father swims at 1.20 meters per second. The question says, how long does it take the father to catch the son? To be clear, when they say how long like that, they're asking you about time. So I want you to try to solve this problem using the original method. Figure out what's the same, figure out what's different, write your relationships, and then go through and solve. I'd like you to pause the video here, and when you hit play, we'll discuss the solution. All right, so as we saw here, this question was asking us, how long does it take the father to catch the son? And your work should look something like this. Now the answer here is 20 seconds, but I'm going to go through the solution now. So in the knowns, I've written down the speed of the father, which is 1.20 meters per second, the speed of the son, which is 0.80 meters per second. And the important thing to realize here is the relationship between the variables distance and time. Now, whether you can see this or not, this thing up here says sun. So the sun is going. from the end of the pool away from the end of the pool. It's at least implied in the problem that the son is going to get caught at some point. While the father waits here for 10 seconds before he starts going, so maybe the son is here when the father begins, he goes and then eventually catches the son. So the location where the problem stops is where the father catches the son. And when the father catches the son, they're in the same location. So they've traveled equal distances. And the fact that they travel equal distances tells you that the times must be different. And of course they are, because the father gave the son a 10-second head start. So I've written here, up at the top, let's see how this laser pointer function works. Ooh, I've written here that the time traveled by the son is equal to the time traveled by the father plus the additional 10 seconds. I hope that makes sense. A head start means you're adding on time because they're traveling for 10 seconds while the father is just sitting there waiting to start. And then, of course, we're looking for the time traveled by the father. By the way, I'm sure you notice I haven't written this on the whiteboard at my desk at home. I bought a little tablet that I can write with a pen on, so I hope this is legible. I promise you it will get neater as I continue to practice with it. So the first line, of course, is that the distance traveled by the father is equal to the distance traveled by the son. Moving on, the substitution of an equation for distance is your next move. So notice over here, I wrote if v is equal to d over t, then obviously basic algebra tells us that d is equal to speed times time. And so I just substituted in speed times time. I got the speed of the father times the time of the father, and then I have the speed of the son times the time of the son. Now, of course, that doesn't really give you anything because we know the velocity, or the speed, of the father, and we know the speed of the son, but we don't know either the time of the son or the time of the father. And so we have to make our substitution here of the time of the son into the equation. Now, it is true that you could have made the alternate substitution. You could have written the time of the father is equal to the time of the son minus 10 seconds. But then what you would end up having left over in the equation would be the time of the son. Now, obviously, that's not that big of a deal. You solve for the time of the son, and then you just take 10 seconds off of it to find the time for the father. But it's always good to think about that a little bit as you go into this here, that whatever you're making your substitution for, which is whatever's on this side of the equal sign, that variable is now going to disappear from the equation. And so the other one, in this case, the time of the father, is what you're going to be solving for. And that's good because that's what the question is actually asking us for. So I took out the time for the son and plugged in the time for the father. I took out the time for the son and plugged in the equation for the time for the son, which is the time for the father plus 10 seconds. So I have speed of the father times the father's time equals son speed times the whole thing, time of the father plus 10 seconds. The key detail here is that you want to distribute the speed of the son to both of those terms. So we have VFTF equals VSTF plus VS times 10 seconds. And then moving on to the next line, notice that term has father's time. This term has the father's time. So I've got to group them on the same side of the equation so I can factor it out. So I've subtracted VSTF over to the other side. So I have father speed, father's time, minus son's speed times the father's time equals VS times 10 seconds. Both of those terms have a TF, so I factored it out. I have TF times VF minus VS equals VS times 10 seconds. And then all I have to do is divide over these difference in speeds to the other side, and I have my equation TF equals Vs times 10 seconds over speed of the father minus the speed of the son. And so you plug it in, 0.8 meters per second times 10 seconds over 1.2 meters per second minus 0.8 meters per second, and that gives you 20 seconds. Now, I think it's a really important thing. I'm actually curious whether any of you did it, but it is important to realize you actually need to think carefully about that answer for a second, because that might not be right. And the reason why that might not be right is because the pool, as they said in the problem, is only 25 meters long. And so we have to make sure if the father has enough room to catch the son. And so the speed of the father is 1.20 meters per second. The speed of the, the time for the father is 20 seconds. And so we want to see how far they're going to go. I already wrote down over here, so I'm going to save the step. If v is equal to d over t, then we already know that d is equal to v times t, right? So I'm just going to sub that in. D equals v times t. And when we take our speed, 1.20 times 20 seconds, then we get 24 meters, which is just enough space for the father to catch the son. But of course, I'm sure some of you explicitly ignored the instructions I gave you, and rather than doing the original method for this problem said, no, I don't want to do the original method. It's so long. I'm just going to do the shortcut. We might as well talk about the shortcut. Obviously, it's good to think about too, just to see how it works, especially because, as I mentioned, the shortcut doesn't really lend itself as nicely to this problem as it did to the last one. Because in the last problem, it was easy because they told us the gap distance. Here, we were not told the gap distance. We were only told the time for the head start that the father gave to the son. So let's take a look at how that would be applied to a problem like this. So obviously in the knowns here, we have the father speed, the son speed. I wrote the gap distance up here. I did show the work for it down there, but that's what you need to solve for the gap time. So the gap distance is 8 meters. I'll tell you how I arrived at that in a second. And then obviously the gap time is what we're looking for here, because that's what they asked for. How long does it take the father to close the gap? And so what do we need to do this gap distance sort of thing? Well, we definitely need the relative velocity. So I just showed the work for that right here. Remember, we said we said just at the beginning of this video that the relative velocity is the difference between their speeds. And so that tells us that the relative velocity is 1.20 meters per second minus 0.8 meters per second. And so that gives us a relative velocity of 0.4 meters per second. But of course, that gives us nothing if we don't have the gap distance. And so using the equation v equals d over t, you can figure out the gap distance if you realize the father gave the son a head start. We know how fast the son was going while he was given that head start. And we know how long the head start was. So simply enough, we take the sun's speed, 0.8 meters per second, times the 10-second head start, and we get that the son was 8 meters ahead of the father once the father started swimming. That 8-meter distance then is the gap distance which the father is closing throughout the trip because he is swimming faster than his son. And so we use the equation relative velocity equals the gap distance over the gap time. And solving for the time gap, we get gap distance over the relative velocity And that gives us 8 meters over 0.4 meters per second, which is, what do you know, 20 seconds. So it's a little bit extra work in the sense that you actually have to find the gap distance here to be able to solve for the thing the problem is actually asking you to solve for, but it's still eminently doable nonetheless. I want to just say one more time, though. If you are avoiding the original method because you think the factoring is annoying or you're having trouble with the factoring or whatever, you can only avoid that for so long in this class, because we are eventually going to need to be able to factor flawlessly 100% of the time. So you might as well start to get the practice in now. Especially because if I give you one of these problems on like a test and I ask you to upload a picture of your work, I could ask you to do both just for fun. So you should be prepared for both. Okay. And so with that, we've gotten to the main focus for today, which is how we can represent motion in a variety of different ways. This is actually a pretty big focus in thinking when they were designing the AP curriculum. Basically, if you remember a few days ago when I showed you all that the list of those science practices, doing algebra was like only one of those things. And what I said was, we want to be able to represent our understanding in a lot of additional ways besides just mashing numbers into equation and getting an answer. So what we are going to talk about right here is the variety of ways you can represent motion, whether that be some sort of diagram or some sort of written explanation or some sort of graph. There are a variety of different ways that you can describe how an object is moving besides simply doing algebra. And one of those ways that you can represent motion is with something called a motion diagram. And so essentially what these motion diagrams are showing you is like a snapshot of the object at different times. And so if we take this one, for example, this is where the object started. Oops. This is where the object started. Then it ended up there, then there, then there, then there, and then there, and so on. And by showing the dots in this way, we get an idea about how the object is moving. So what can we say about these motion diagrams? Well, the first thing, I want you to actually look at that heading there. Notice it says motion diagrams particle model. Throughout the year, we also want to focus on the fact that what we are doing is we are creating models for understanding something. And that's actually how most of physics is done. Right? When we are talking about like the motion of a car or something in this class, we're really not talking about the motion of a car. We are approximating the motion of a car, because cars experience an enormous amount of extra forces than the forces we generally consider in these problems. We don't talk about air resistance. We don't really talk about what's happening between the tire and the ground. We don't really talk about rolling friction that much. And so the idea here is, when we are doing these problems, we are trying to simplify them and imagine that this car, which is this big and complex machine, is really actually just a single point located in space, which is traveling with all of the characteristics that the problem is saying this imaginary car has. So the idea is, all of the things we are about to say here are all based on the assumption that when we are looking at the motion of objects, we are considering them to be particles with all of the mass, like the mass of a car is like 2,000 kilograms or whatever, maybe 3,000, all of that mass located and concentrated at one particular point in space. And we replace the car in our model with a tiny particle that has a mass of however many kilograms the car has, and treat it like that. That's the idea for why that says the particle model. And I want you to keep that in mind as we go through the year, because we are going to come back to this idea that we don't really necessarily have a perfect understanding for all of the processes that we'll be looking at this year, but rather we will be sort of simplifying them and quote unquote modeling them as we go along. All right, so first little bit there, a motion diagram shows the position of an object at successive times. That's it, really. It just shows you where the object is at successive times. So, series of dots are drawn to represent the object. We use a series of dots to represent the object. The dots, which are representing the position of the object, are shown at successive time intervals which are equal. And that's super important. The time interval shown in all of these diagrams is equal. The time intervals are equal. So the idea is, by making the time intervals equal, we can get a sense of the rate of change of position, or in other words, the speed. So the spacing of the particles, because we are getting a sense of the rate of change of the position, is in fact telling us about the motion of the objects. This part is very important. So important that I'm going to laser it. The first dot always shows the object at time t equals 0. That means the first dot is showing you where the object was before anything happened. That's super crucially important. If you want to find out what happened during any amount of time, then you have to involve multiple dots. If you want to find out where an object is at a particular time, then you always need to remember that the first dot shows you time t equals 0. That's a super easy mistake to make, because a lot of people look at the problem and it'll say something like, where was the object located after 2 seconds? And you'll end up looking at the second dot. Well, if the first dot is showing you time t equals 0, the second dot is showing you time t equals 1 second. So that means you got to look at the third dot to show time t equals 2 seconds. And here's a typical example of a motion diagram, which we're going to get to. But let me just jump back here for a second and say, if you want to pause this video and write that down, go ahead and do that. When you hit play, we'll jump into an example. Okay, so let me just address this for a second. The worksheet, which is posted in the stream on Google Classroom, which says motion diagrams, is where this problem comes from. If you'd like, I suggest you go to the stream, open it up. If you want to print it out for yourself, you can go ahead. If we were all in school, I would have given you a printed copy of this sheet. These worksheets that I'm going to end up posting for you all come from a book called Tippers, or at least that's how they say it. I think it's supposed to be pronounced typers based on, English. But it's an acronym. It stands for Tasks Inspired by Physics Education Research. And essentially what these people who've written this book have concluded is that when you look at the way people learn physics, you notice some patterns. And when you give them certain kinds of tasks to do, they learn physics better. And we're going to do a ton of problems out of this book because they're great. They all have codes. B1 stands for mechanics. We're going to be doing B1 problems for like many, many months. And these codes here usually tell you what kind of problem it is. So this kind of problem is called a ranking task, because notice they're asking you to rank. So it says, in each case, a sphere is moving from left to right next to a tape marked in meters. Notice moving from left to right is really important information. It says a strobe or flash photograph is taken every second and the location of the sphere is recorded. The total time intervals shown are not the same for all the spheres. This is a time in the period when I usually like to ask, looking at those diagrams, how do you know that that's true? How do you know that the time intervals shown are not the same for all the spheres? And if you notice, you could figure that out by the number of dots. As we said, the first dot shows t equals 0. The second dot shows t equals 1, and so on. So if you count up the number of dots, if you subtract 1, that's the number of seconds. And the basic idea here is because the number of dots are different, then the time is different. So I want to show you how to do this first one, or at least like the way I think about it, and then have you look at another one on your own. Because interpreting these motion diagrams is something that is pretty important. So this problem here says rank the magnitude of the displacement over the first 3 seconds. I'm going to change the color of this actually. So the first thing you need to do, obviously, because we're finding displacement, is you need to recognize the fact that displacement, delta x, is equal to the final position minus the initial position. So we need to look at the object where it starts and look at the object after 3 seconds. I'm sure I know what you're thinking. You're thinking that's where I go. But remember, the first dot is t equals 0. That's t equals 1, t equals 2, t equals 3. The fourth dot is what we're looking at. So to find the displacement, you take the final position minus the initial position. Final position is 6, the initial position is 0, and so 6 minus 0 is 6 meters. Moving on to B, that's where we start. 2, 3, 4, that's our fourth dot. And so 2 minus 0 gives us a displacement of 2 meters. Looking at C, that's where it starts, so that's 2, 3, 4. 9 minus 0 is 9. And then looking at D, this is the one where I think people get confused. You have to be careful of this. Remember, these are tasks inspired by physics education research. Why do you think they gave you 3 examples in a row where the object was starting at 0, and then the fourth example, the object is starting at 1? That's because people who know less physics than you guys are just looking at where the fourth dot is and saying, oh, that's how far it got, 6 meters, 2 meters, 9 meters. That's not what displacement means. Displacement is the change in position. And so you have to subtract the final and the initial position. So our initial position is at 1. So that's our first dot, second dot, third dot, fourth dot. It ends up at 10. And the final position, 10 meters, minus the initial position, 1 meter, is, you guessed it, 9 meters. Now, some of you might have seen this in the homework solution from Wednesday. I put a ranking And in between two numbers that were ranked the same, I just put equals. This is going to be something that comes up a lot this year. So keep this in mind. When you do these rankings, it's very important to pay attention to these boxes because they tell you greatest or least. And then you just put in the appropriate answer. So whether you put C or D, it doesn't really matter. First, I'm just going to do a D. And then I'm going to put C. That would suggest that D is greater than C. D is not greater than C. So you just put an equal sign between them. That's it. You just indicate they're equal. D equals C, then A, then B. Now, when you have these boxes for rankings, which I've actually been inserting into questions in recent years just because I think it helps, because on the AP test, they have something very similar. It's like lines. They have like these lines 1, 2, 3, 4, and they have them labeled like 1, 2, 3, 4, and you can put equal signs between them too. They explicitly tell you to do that in the instructions, but it's important to realize you don't need lines for this. Like you can just write D equals C, which is greater than A, which is greater than B, and you can tell from the greater than or less than or greater than signs, depending on how you write them, which one is greater and which one is least. And so that's the idea. These things always have underneath too and explain your reasoning part. And so I would say here displacement is the difference between x final and x naught. And again, we're not looking to write like a paragraph here. Obviously, you can write this much more beautifully than that, but that's not what we're focused on for these. These sheets are really just going to be used to like help you prepare for tests. And you want to just make like quick notes for yourself. You could even just write the equation there too, but generally I like you to write at least a little more than that. And then something else that we should also probably write to remind ourselves about these things is dot number 1 shows object at t equals 0 seconds. So for 3 seconds, you'll look at the fourth dot. All right, so notice this particular problem involved you in ranking displacement. Now that we've finished up that one, I'd like you to go ahead and try the next one on your own. This is on that same worksheet, but it's RT04. So ranking task number 4. Same directions in each case. A sphere is moving from left to right next to a tape marked in meters. A strobe flash photograph is taken every second. And the location of the sphere is recorded. The total time intervals are not the same for all the spheres. I'd like you to take a minute to go through this one, and as they ask you to, rank the magnitude of the average velocity. We'll go over the answer here in a moment once you hit play. So pause this video here, and when you hit play, we'll talk about the answer. All right, so as it says here, in each case, a sphere is moving from left to right next to a tape marked in meters. We've got the same setup as we've got last time. The difference here is that the problem says we got to rank the magnitude of the average velocity over the first 2 seconds. So the way I approached this, and I hope the way you approached this, was I just went through and I went to the third dot. Remember, it's the third dot here that shows you the second. And I just marked off where all the objects or all the diagrams, third dot was. And then I just looked, and we could zip through this real fast. We can say 4 minus 0 is 4. 1 minus 0 is 1. 6 minus 0 is 6. And then, of course, 9 minus 1 is 8. What does that give us, though? That gives us the displacement. They did not ask us about the displacement. They asked us about the average velocity. So you could just go ahead and calculate the average velocity by taking all of those displacements and dividing them by the times, and then you can rank them. But of course, that's not really the way I want you to do this problem. Because the way we are going to go about doing these problems as we move on through the year is by trying to do things without necessarily always having to calculate them, right? Like if you need to bail yourself out in a ranking task and it says rank these things and you don't know the shortcut and you just have to brute force them and calculate every single one and write down the answers and then rank the answers, do it. But you don't have to, is the point. If you think about it in terms of the equation. The equation that you're going to use is going to be v, the velocity, is equal to the displacement over time. And if the times in the equation are all the same, that means no matter what, the larger displacement is going to produce the larger average speed. And that's the idea behind this question, the answer to this question. So what I wrote here was I filled in the displacements, and then I ranked them in terms of the displacements. D had the largest displacement, then C, then A, then B. And what I wrote here is that for equal time intervals, the velocity is equal to the equation velocity equals delta x over t tells us that the velocity, let me put the arrow over that velocity, is directly proportional to x. So a larger delta x gives me a larger velocity. Now let me just write this over here where I may have some space. For our purposes, we are going to be saying things like these variables are directly proportional a lot. And so to save time, the symbol alpha, which is a Greek letter, it's basically like a fish, means directly proportional. So I hope that makes sense to you, because we are going to be doing a lot of this kind of thinking a ton this year, saying that if two variables are proportional, one gets bigger, the other gets bigger. If two variables are inversely proportional, one gets bigger, the other gets smaller, etc., etc. So this is something you should be prepared for, and I hope thinking about this makes sense, particularly the part that this is only true if the times are the same. The other variables being held constant is really the only way that this argument works, right? Because like if I go 10 meters and you go 5 meters, that doesn't necessarily mean I have a larger velocity. That would only be true if the times during which we experience those displacements were the same. Because if I go 10 meters in 4 seconds and you go 5 meters in 1 second, you're actually going twice as fast as me. I feel like you guys probably didn't need that explained to you, but I feel the need to because I can't see how your faces are reacting to what I'm saying. So anyway, if you have any questions about that, just let me know. The next way we represent motion, besides with these motion diagrams, is probably going to look pretty familiar to you after the honors class. You guessed it, graphs. Graphs are our friend. Don't forget that. Now, these graphs, as you can see here, which notice this is in the second worksheet now that was attached to the post in your Google Classroom stream, this document has a ranking task on it that says B1RT13. And as you can see, this particular ranking task says these 4 graphs are position versus time graphs. We really never saw these in honors physics. What we saw in honors physics are displacement versus time graphs, which are kind of silly because it says here, if your displacement is like instantaneously 8, displacement is something that happens over time. It can't really just be instantaneously 8 before any amount of time passes. It's kind of a weird way to put it. For some reason, the Regents curriculum assumes that like position is just like a hard concept for you to understand, despite the fact that it's just where an object is located, and that's really all that there is to it. But we're going to be using these position versus time graphs a bunch this year. And it says you got these graphs which are showing you the position as a function of time, and the question is asking you to rank the magnitude of the displacement during the time interval from 0 to 4 seconds. There's really not a whole lot that needs to be said about this. Take a second to pause this video. We've talked about displacement a decent amount already this year. The fact that this is represented on a graph shouldn't be too hard for you. So take a second to pause this, come up with your ranking, and maybe write a little something for the explain your reasoning bit. And when you hit play, we'll go over it. So this is the first problem where I'm probably going to explain to you that a good way to do these rankings is to actually think about the explanation first. Because if you try to force a ranking without having a clear understanding of what you're doing, your ranking is probably going to be wrong. So for the ranking, we can just say pretty simply here, displacement is the change in position. And I'm going to put there in parentheses delta x. So looking at A, final position, final position 6 meters, initial position 6 meters, change in position 0 meters. This one ends up at 6, starts at 2. 6 minus 2 is 4 meters. This one goes all 8 meters. And this one starts at 0, ends at 0. So that would be 0 meters. And so for our ranking, pretty simply here, we have C, then B, and then A is equal to D. And that's it. Reading and interpreting these graphs is not that complicated. You just have to remember what the graph is showing you and how the thing they're asking you for, in this case displacement, is related to the thing they're showing you. I'd like everybody to take a second, though, to consider an alternative version of this question. What if instead of asking you rank the magnitude of the displacement during the time interval from 0 to 4, it said rank the distance traveled during the time interval from 0 to 4? That's what I want to think about next. But first, I just realized I didn't say something. Notice, every year in class, the fact that this object starts at 8 and ends at 0 means the displacement is actually negative 8. But since the problem just says magnitude, you don't really need to worry about that. Sometimes it doesn't say magnitude, and so negative you would consider to be the least. But almost all the time, it's going to say the magnitude of something that could be negative if it is negative. I want you to take a second to pause this video and think about how the ranking for the distance would work out. And when you hit play, we'll go over it. All right, so remember here, while displacement is the change in position, distance is just the length of the path. Now, obviously for A, this is trivial because it doesn't go anywhere. So that one's still 0. B is walking in a straight line, and so the distance is still 4 meters. C, the only difference is that instead of being -8, it's positive, because distance is a scalar, which doesn't account for directional information. The hard one here, I think, is D. And the only reason why the hard one here is this graph is because when the object is traveling from 0 to 2 seconds, its displacement is 8 meters. And when it travels back to the origin from 2 to 4, its displacement is -8, and so those displacements cancel each other out. But in terms of distance, it does not cancel, because distance is a scalar, which means your distance can never decrease. So the distance goes up by 8 from 0 to 2, and it goes up by another 8 from 0 to 4. And so that would make our ranking here D, then C, then B, then A. And that would only be if it said rank the distance. Now, the problem didn't actually say that, but I think that's always good to think about to make sure we really understand the difference between distance and displacement. So let's just say 2 quick things about this graph. First, since displacement is defined as the change in position, to find displacement from the graph, you just subtract the y-coordinates for 2 different points, really 2 different times. Displacement is defined as the change in position. So you just subtract final and initial position, piece of cake. Distance, on the other hand, is a scalar. So to find the distance from the graph, we have to add the lengths of each individual segment of the graph. Or in other words, the absolute value of each individual displacement. All right, let's just take a look at one more of these before we wrap it up for the day. This one here says position versus time graphs average speed. And it says each graph below shows the position of an object as a function of time. I'd like you to take a minute, think about how you could go ahead and answer this, and then we'll get into another important concept about position versus time graphs related to this problem. Okay, so obviously here, since this thing has a displacement of 0, its average speed is 0 meters per second. This one is a little tricky, as we said, because it experiences this positive displacement for the first 2 seconds and then the negative displacement for the second 2 seconds. And so this one has a distance of 16 meters in a time of 4 seconds, and so clearly the speed is 4 meters per second. And so I also would hope what is clear to everybody is that that one is clearly going to be the largest. And so we'll just put D down for this one. A is certainly going to be the smallest. And so now we'll fill in the other 2. There are a couple of ways you could do this. You could subtract the final position, the initial position, and then divide it by the final time and the initial time. And what you'd be doing there is you'd be finding the slope. Notice here, it's the same thing for C as well, but for C, the slope is negative. And so here, because they're asking us for speed, we don't care about the sign of the slope, because speed is a scalar. So clearly, from looking at it, C has a larger slope than B, and so the answer would be DCBA. And the point we'll put here is the magnitude of the slope for a position versus time graph is the speed. And that brings us to the last little bit for today. Position versus time graphs are going to be used a ton in this class. You want to remember this bit about the slope. It should make sense to everybody that slope is a measurement of rates of change. And because what the quantity we are talking about here is position, if we are talking about how the position is changing, we're talking about the displacement. And if we're talking about how the position is changing per unit time, that is literally the definition of velocity. And if we're taking the magnitude of that, then that's the speed. So let's write a couple of notes here. Since the slope is defined as the average rate of change, and the average velocity is defined as the average rate of change of the position, the slope of the graph of the position versus time is the object's velocity. And we'll just mark here as well, of course, that the magnitude is the speed. The only part you have to be careful of there then are the graphs when the displacement goes up, or I should say the position versus time graph shows the position increasing and then decreasing. Because then really what you need to do is you need to take the magnitudes of the individual slopes and then essentially apply this formula by adding all those individual distances together. But that's the basic idea. As we get further into more complicated kinds of motion, we will start to introduce more graphs. But for now, since we're just talking about velocity, and we're really dealing with constant velocity motion, we'll only introduce the position versus time graph. And with that, that's it for constant velocity. Which brings us to accelerated motion. We did not explicitly define this as such today, or any other day, but constant velocity motion is generally referred to as uniform linear motion. And so what we can say about uniform linear motion is motion in a straight line at a constant velocity. Since the velocity of the object is constant, of course, the object will travel an equal amount of distance during each successive time interval. That's what constant velocity motion means, right? If it's going, X meters per second, like let's say 5 meters per second, that means every second it's going the same 5 meters. Simple. Non-uniform linear motion is motion in a straight line at a changing velocity, and that's the difference. This bit is very important, that we are going to assume here that these velocities are changing at constant rates. And the reason why that's important is because if the velocity of an object is not changing at a constant rate, then we need calculus. The fact that it will be changing at a constant rate means we can simply use algebra. Since the velocity of the object is changing, the important point here is the distance that the object travels during each second will be different. And so if it's speeding up, it'll travel more distance each second. And if it's slowing down, it'll travel less distance each second. And the last point, when we use the term acceleration in physics, it does not simply imply speeding up, but rather any change in velocity in any direction. In the common lexicon, we have the words acceleration and deceleration. But what we consider, like normal people consider to be acceleration and deceleration in physics, are just both examples of plain old acceleration. And with that, we're now ready to address the equations of accelerated motion. Equations for accelerated motion, if you remember from honors physics, are called kinematic equations. And the kinematic equations are a group of physics equations which will allow us to describe the motion of moving objects. And that's actually true whether they're moving at a constant velocity or if they're accelerating. And because we're going to need to have a lengthy discussion about those equations, we'll save that for Tuesday. That's it for the week. Enjoy the weekend, everybody.